In this video, we're going to cover the fundamental theorem of calculus, part 1. And just as a reminder, let's recall that we defined our definite integral from a to b of f of x dx as the limit, as n goes to infinity, of the summation from k equals 1 to n of f of x sub k star, which is just some x value in the kth interval, times delta x sub k, which is the width of that kth interval. Right? So we took the summation of this from k equals 1 to n, and then we take the limit as n goes to infinity of that summation. And that is how we defined our definite integral from a to b, provided this limit exists. All right. Now, the problem is, this is often quite difficult. Difficult enough that we don't want to be calculating this limit if we can help it. So, we want to think of what else we might be able to do this, or how else we might be able to calculate this limit, right? This limit was how we determined our area under the curve, which is the problem that we wanted to answer. So, what can we do? Well, the first thing is we can think of the definite integral as a function of x representing the area so far. And I will explain what that means here in just a moment via a picture. But first, let's suppose that f of t is an integrable function over the interval t equals a to t equals b. All right, now let's draw the picture of what's going on here. So we have some function f of t from t equals a to t equals b. And then, if we're taking the definite integral over this region, we calculate this limit up here. But another thing that we can think about is, well, what if we wanted to take the definite integral to some point t equals x between a and b? Well, if we do that, then we can actually define a function that represents this area, the shaded region, the area of the shaded region. And that is the function capital F of x equal to the integral from a to x of f of t dt, using our integral notation that we came up with or introduced in the previous video. All right. So here is our function to represent the area so far, right? As x changes here, this gives us a function that will output the area under the curve from a to x. All right. So what are we trying to do? We're trying to see if we can come up with what this function is, right? If we can come up with what this function is, then we have a way to solve our limit without having to solve the limit, without having to find that limit, which is going to be, again, quite difficult most of the time. So our goal is to come up with a formula for this. And here's how we're going to do that. let's ask ourselves, what happens when we take the derivative of this function? That function that we just created. Oops, there we go. What happens when we take the derivative of this function? So let's consider the geometry of the problem. Okay, so let's draw our picture again. Something like this, from t equals a to t equals b. And we're going to define some x value here, and then we're going to define some x plus h value here. And we're going to look at the area of a rectangle from x to x plus h. What is h? H is just some small value that we add to x here. And now let's think about what we actually want here. The area here from a to x plus h is exactly f of x plus h. And then if we subtract off the area from a to x, which by the way would be f of x by how we defined this function, what is that? Well, that area would be the area of this little sliver here. But what is that approximately equal to? That is approximately equal to the area of this rectangle, which is the width h times the height, and the height is our function f of x. Or really, we'll call it f of x. Right, is the height of the function when you evaluate it at x. And of course, this is an approximation, right? It's not exact here. But as h goes to 0, as in the width of this gets narrower and narrower, those areas will certainly get closer and closer to each other. So as h gets really small, then this equality is true. In other words, the derivative, if we take the derivative of this capital F of x, notice that this is the limit as h goes to 0 of capital F of x plus h minus f of x, capital F of x all over h. But if we divide by h on both sides here, what does this equal? This is equal to, with our approximation up here, f of x, right? This is approximately true, and it gets more and more true as h goes to 0, which is exactly what we're doing here when we come up with the derivative of this capital F of x function, right? And again, what was this? This capital F of x was our area function. And when we take the derivative of that, we get just our original function here, f of x. And really, we haven't proven this yet, but this picture and this thought process and argument tells us, or at least gives us a reason to believe, the following. And the following is what we call the fundamental theorem of calculus, part 1. And here it is. If f is continuous on the closed interval a to b, then capital F of x is equal to this definite integral from a to x of f of t dt. This function is continuous on the closed interval a to b and differentiable on the open interval a to b, and furthermore, its derivative is f of x, lowercase f of x, which is this function f of t, but evaluated at x. So let's write that out. F prime of x, which is the derivative of this integral from a to x of f of t dt, is f of x. So this function that we had in here, but evaluated with our variable at x. So what does this say? This tells us that the derivative undoes this idea of an integral here. So really, those are inverse operations, sort of. And that is going to give us a path for calculating our integrals, which happen to be antiderivatives. Since we take a derivative to get back to here, if we wanted to go back to this thing in here, we would find the antiderivative of this function, right? And that would go back to this function inside, which is our definite integral function for our area under the curve. All right, and that is where we will end this video. Stay tuned for the next video where we will use this theorem and try to get a little bit more understanding about what that means.